Hi everyone, thank you for the introduction. I am Erkut from the Bilkent University from Turkey. We are working on the ASE light sources under the leadership of the Professor Özbay and very talented colleagues, Dr. Yertutanol and Dr. Andaç. And today I am going to talk about the optimization of the ASE light sources designed for enhancement of wavelength stability. Here is my outline. Firstly, I will introduce our topic and I will introduce the ASE light sources application areas. After that, I will specify the topic, which is one of the application areas of the ASE light sources, interferometric fiber optic gyroscopes. Briefly, I will summarize the working principle of the interferometric fiber optic gyroscopes and importance of the wavelength stability of the IFERs. So then I will continue with our objectives, our motivation, and our starting point, what we did for the enhancement of the wavelength stability. And then I will compare the two ASE light sources. One of them is the traditional one, and the other one is our novel design. I will share all the theoretical and experimental results of these two configurations. So still we are working on the improvement of the enhancement of the wavelength stability. I will explain the future implications, and then I will conclude my presentation, and it will be end of my presentation. So let's start with the introduction. ASE light sources in today's source are very popular in which fields? Fields of the optical communication, spectroscopy, sensing systems, and industrial and military applications. It is important for the optical communications. For what specifications? The specifications are the stable and continuous source. For the optical communications, these two subjects is so critical. So ASE light sources are very popular because of these two specifications. Another one is the spectroscopy. In the spectroscopy fields, to get better resolution, you have to get a higher output. Your light source must have higher output. So for the higher output, the ASE light sources are much better than the other sources. By the way, also SLD light sources are used in this field, but due to the low optical power, ASE light sources are preferred much more. The other application areas is the sensing systems. For this, we are all listening to the presentation about the distribution systems. ASE light sources are using also in this field for the detection of the temperature, strain, or chemical change. So I will specify the topic, as I mentioned, the industrial and military applications. We are working on the topic, particularly inertial navigation system. So the most popular inertial navigation system is the fiber optic gyroscopes. If we briefly summarize the basics of the interferometric gyroscopes, in the schematic, you can see that the basic configuration consists of two components. The first one is the ASE light sources. The second one is the multifunctional integrated optical chip MIOC. The third one is the most important component, the sensing element of the fiber optic gyroscopes, the fiber coil. This is the single-axis gyro configuration. One can want to work on 3 axes. You can supply with these light sources for 3 axes because, as I mentioned earlier, the light source has high optical power to feed all the 3 axes. The fiber coil is so important. That is why it's so important, because the sensing element of the fiber optic gyroscope is the fiber coil. Also, these interferometric fiber optic gyroscopes are classified according to the length of the fiber coil. When the fiber coil's length getting higher and higher, you get better sensitivity and accuracy. So ASE light sources basically Before that, another important point of the fiber optic gyroscope is the wavelength stability of the ASE light sources, because this is directly related with the sensitivity of the fiber optic gyroscopes. In the formula, you can see that the term is called as a scale factor. It represents the sensitivity of the fiber optic gyroscopes. It is directly related with the wavelength change of the light source you use. So how much stable light source, it means get higher and stable and precision measurement. So this is why it's so important to improve wavelength stability for the fiber optic gyroscopes. So what we did for the enhancement of the wavelength stability, I will mention that our objectives was to enhance the wavelength stability. So for these purposes, we started the literature review, and we conducted a comprehensive literature review. So according to those informations, we studied the theory of the ASE light sources, and then quickly we also conducted experimental investigations. So as a result of this experimental work, we succeed that our experimental investigations resulting in a almost 60% enhancement in the wavelength stability. In the next few slides, I will share the details of our work. But before, I want to introduce the basics of the traditional ASE light sources. In the figure, we can see the basic components of the ASE light source. The first component is our laser diode. Other component is the WDM with the isolator. This is a hybrid component integrated with the isolator, and also we are using the erbium lobe fiber. So these three components are the basics of the ASE light source. And in the left side, you can see that the energy level diagrams of the erbium fiber. The erbium fiber is so important for the ASE light sources. That is why when we check the energy level diagram of the erbium fiber, we see that when we stimulate the erbium ions with the 980 nanometer pump, the energy level of the erbium ions are changing, go through the unstable short lifetime state. But as I understood from the name, this is a short lifetime. They are always tend to back to their ground state. But when they returning to their ground state, they emits 15 and 50 nanometer light. So these lights goes through from the double beam signal, and as I said, it is 15 and 50 nanometer. So the temperature stability is directly dependent with the temperature change of the components you use in the schematic. You can see the formula. The central wavelength of the ASE light source directly related with the erbium ions temperature change, pump power versus wavelength change, pump power versus temperature change, temperature change versus pump wavelength versus temperature change. When we substitute the real values in the formula, the second and third terms are become negligible. So the most important effect on the wavelength stability coming from the wavelength change of the erbium fiber. So you firstly, if you want to get better wavelength stability, you should reduce the effect of the temperature change of the erbium fiber. So with these purposes, we construct the traditional ASE light sources. When we check the literature, always we faced with this basic configuration. After we construct this configuration, we get some measurements in the room temperature and according to temperature. So one can ask that, how did you determine the length of the erbium fiber? Before the experimental work for the determining the erbium length fiber, in the simulation environment, by simulation programming, we optimize the erbium length of the ASE light sources. We observe that when the fiber length of the erbium length fiber gets 10 meter, our optical power gets saturated. So we choose for the traditional ASE light sources, we use the 10 meter erbium fiber. By the way, as you see, we have two ends for the erbium fiber. One of them goes through the IEEE, the other one is terminated. How can we terminate these ends? We terminate it with the node termination method. So, after determining the length of the erbium, we'll continue with the get some measurements. Firstly, we measure the spectrum of our traditional light sources. As you see in the left figure, we get this measurement in the room temperature. We have two humped spectrum. One hump comes from the absorption characteristic of the erbium fiber. The second one due to the emission of the erbium fiber, and this is our central wavelength. And our central wavelength is 15 and 48 nanometer. So we also observe that the absorption, the hump due to the absorption, is more sensitive than the emission hump. So our aim was eliminating the absorption hump of the spectrum. So for this configuration, we also conducted in the temperature test. In the climatic cabin, we tested our ASE light source. In the temperature range -10 to 60, we get 12 part per million ppm wavelength stability. In the later works, we enhance this wavelength stability. But how we did, I will explain now. We get some novel approach to design. If you remember from the previous slides, our erbium fibers, one of our erbium fibers, and is terminated. Instead of terminating, we choose using the FPGA and Faraday mirror for the termination end of the erbium fiber. Our aim was using the Faraday mirror, increasing the transmission, increasing the reflection. So in this way, we can reduce the absorption. So with this configuration, also we added some erbium fiber in the signal port of the IEEE, because without need any optical component, we want to filter our wavelength. So in a similar way, we get some spectrum analysis in the room temperature and get some measurements according to temperature. So as you see, we succeed the absorption hump eliminated, and our central wavelength was shifted to L band. So this behaves much more stable in the same temperature range, -1 to 60. So we get the 5.3 part per million wavelength stability. So the components we used for the novel design, we used the filter erbium fiber break grating, and Faraday mirror. All of them, a combination of all of them gets so resulted in a much better wavelength stability. So the filter erbium of the fiber, we filtered unwanted noises, and so we get a clean and more stable output spectrum. With the fiber grating, we used to use 5% reflectivity fiber grating. So this is also we get stable output wavelength. In a similar way, using the Faraday mirror, we prevent the back reflection and get stable output wavelength. As a reminder, significance of the improved stability, as I mentioned before, how much stable wavelength our interferometric gyroscopes sensitivity gets much better. When we compare the traditional one and our novel design, we get 60% enhancement in the wavelength stability. We reduce 12 ppm to 5.3 ppm. So to sum up, we get enhancement in the spectrum. We get a Gaussian distribution spectrum with our novel design. Another one is optical power. For novel design, only 2% loss we get. Another one, and the most important one, is the wavelength stability. We reduce 12 ppm to 5.3 ppm. And also, this is applicable for the interferometric fiber optic gyroscopes. We are still working on these configurations. Our aim is get much better wavelength stability. What's our plan? We are planning to use different fiber ratings, different length of the gain and filter erbium of fibers, and we're using some special filters. So here is my references, and thank you for your time and interest. If you have